All right, all you B.Pharm students and future pharmacists out there, welcome. Today, we're diving deep into something you'll deal with all the time, creating the perfect liquid medicine. We're talking about flocculated versus DeFlocculated suspensions. So, let's start with a problem every pharmacist dreads. You know what I'm talking about, right? You grab a bottle of antacid or an antibiotic, and the medicine has settled into this hard, concrete-like cake at the bottom. And let me tell you, that's not just an inconvenience. It's a complete failure of the formulation.
Okay, so to really get a handle on this, we gotta be on the same page about what a suspension even is. It's pretty simple. You have solid drug particles that don't dissolve, just floating around in a liquid. But here's the catch. These particles are heavy enough that gravity is their worst enemy. They are always going to settle. The whole game is about controlling how they settle.
Now, let's look at the first way you might try to fix this. On the surface, it seems like the perfect solution. It's called the DeFlocculated approach, and the goal is simple. Just keep the particles from sticking together and make them settle as slowly as humanly possible. Sounds perfect, right? Well, let's see about that.
So with this DeFlocculated system, the individual particles settle out really slowly. Cosmetically, it looks fantastic. The liquid stays uniform and cloudy for a long time. But, and this is a huge but, look at what happens in the end. They form this dense, compact sediment. We call that caking, and as you can see, trying to break that up with a simple shake is, well, it's pretty much impossible.
So why does this happen? What's the science here? It's all about electricity, really. In a deflocculated system, every single particle has a strong surface charge that makes it push away all the other particles. It's like having thousands of tiny little magnets all repelling each other. This keeps them separate, sure, but it also lets them slip right past each other and pack down into the tightest, densest formation possible at the bottom. Think of it like sand being perfectly compacted.
Okay, so if keeping particles separate leads to an unusable brick of medicine, what's the alternative? This might sound a little weird. Instead of stopping the particles from touching, we actually encourage them to get together. This is the flocculated approach, and it is our counterintuitive hero.
Just look at the difference here. It's night and day. You can see the particles form these loose little clumps, which we call flocks. Now they do settle fast, and the liquid on top gets clear. But here's the magic. The sediment they form is big, light, and fluffy. It doesn't form a hard cake at all. And the best part? It's incredibly easy to redisperse with just a gentle shake.
The mechanism here is the total opposite of what we saw before. We intentionally dial down those repulsive forces between the particles. This allows weaker attractive forces to gently pull them into these loose, airy clumps. So instead of tightly packed sand, think more like loosely fallen snowflakes. They create this big, porous structure at the bottom that doesn't compact down and can be broken up in a second. This table just lays it all out so clearly. You can see the pros and cons side by side. What's really fascinating is how the supposed disadvantage of the flocculated system, that fast sedimentation rate, is directly responsible for its biggest advantage, being easy to redisperse. And for a patient, being able to actually shake up their medicine is way more important than how pretty it looks sitting on the shelf.
So here's the crucial point. In the real world of making pharmaceuticals, you don't just pick one or the other. You don't just join Team Flocculated or Team DeFlocculated. The best formulators, the real masters of this science, figure out how to get the advantages of both. And this, right here, is the key takeaway. The gold standard in this field is something called controlled flocculation. The idea is to create those nice fluffy flocks that prevent caking, but also to slow down how quickly they settle to the bottom. It's all about finding that perfect, elegant balance.
So how do you actually do this in a lab? Well, here's the playbook. First, you make sure the drug particles are properly wetted and spread out. Then, you add just the right amount of a flocculating agent, something like an electrolyte, to create those loose clumps. Finally, and this is the secret sauce, you add a suspending agent. This basically makes the liquid thicker, it increases the viscosity, and that physically slows down the settling of your brand new flocks.
Okay, this is all really cool science, but why does it matter so much for you as a future pharmacist? The answer comes down to two things that are at the absolute core of your profession: patient safety and making sure the treatment actually works.
This one sentence from a textbook pretty much says it all. A suspension that cakes is, by definition, a failure. It is unstable. It doesn't matter if the drug itself is chemically perfect. If the patient can't get it out of the bottle correctly, the medicine has failed.
And this really shows you the real-world consequences. Just imagine a caked antibiotic suspension. The first few doses the patient takes are going to be mostly liquid with very little drug, so they're getting underdosed. But those last few doses from that sludge at the bottom, they could be dangerously concentrated. That's a potential overdose. It is a direct threat to patient safety and effectiveness.
So I'll leave you with this final thought. The next time you pick up a bottle of calamine lotion or an antacid and give it that good shake, remember what you're actually doing. You're not just mixing a liquid. You are applying physical energy to overcome electrostatic forces, to break down carefully engineered floccules, and to ensure that the next dose delivered is both safe and effective. In that moment, you are controlling the very science we just talked about.